Welcome, everyone, to the Enhancing Clinical Practice and Outcome stream, SNOMED-CT Expo 2022. My name is Nick Egerhaus, and I'm the Global Vendor Engagement Lead and Customer Relations Executive for the Middle East and Africa with SNOMED International, and I'll be moderating today's session. All questions will be answered at the conclusion of the presentation, and online attendees, please use the Q&A box to type your questions to the presenter. On-site attendees, I'll be handing out a microphone in the room if you have any questions. I think we've clearly left the best for last. It's the last presentation of the day and of the conference. I'm pleased to introduce Erin Holmes from Babylon Health, who will be presenting using SNOMED-CT at Babylon, creating a shared understanding of clinical meaning to power artificial intelligence and improved health outcomes. Michael Lawley always makes an entrance. Erin, over to you.
Thank you very much. Thank you, Nick. And thank you everyone for joining me for the very last session of the day. I do appreciate it. As Nick has kindly introduced, I am Erin Holmes. I'm the Senior Clinical Informatician for Babylon Health, which I will introduce to you in just a moment, but I'm going to be double clicking, so bear with me. Okay. Just a little bit of background, which I'm sure you're all aware of. If not before, then definitely by the end of this conference. But at all levels of the healthcare system, health professionals are responsible for different kinds of information, such as the patient's medical history, the diagnosis, prescriptions related data, the medical and clinical data, like data from imaging and laboratory examinations, and many others. EMRs, personal health records, medical practice management software, and many other healthcare data components collectively have the potential to improve the quality, service efficiency, and costs of healthcare, along with the reduction of medical errors compared to their paper-based predecessors. Data in healthcare also includes the healthcare payer provider data, pharmacy prescriptions, insurance records, the development of usage of wellness monitoring devices and related software that can generate alerts and share the health-related data of a patient with the respective healthcare providers has gained momentum, especially in establishing a real-time biomedical and health monitoring system. These devices are generating a huge amount of data that can be analyzed to provide real-time clinical care. One of our core missions at Babylon is to deliver affordable and accessible healthcare to every human being on the planet. Huge, right? Very ambitious, but I will tell you how we do that in a moment. Part of that starts with a digital first approach and our ability to ingest as much data as humanly possible. Now, at this point, I would be playing you a video. It would have some really great music. It'd get you all fired up for the last session, but unfortunately it's not playing. So instead you get to hear me narrate a very short version of it. In short, it's a move from relative sick care to proactive healthcare. We use AI to predict outcomes, to prevent issues before they arise, and personalize in real time. We connect patients to care in real time to fulfill our mission of providing high quality healthcare accessible and affordable to everyone. Unfortunately, the video was a lot more exciting than that, but here we go. In the healthcare industry, primarily data has been structured in a very siloed way. It's collected from disparate sources, unstructured and structured. So at Babylon, we've taken an approach we call the health graph. Health graph is core to what we do in our data platform, essentially bringing across multiple domains of knowledge, creating an ontology or knowledge on top of those data sets, and then using those data sets to then power the training models that run our business. Health graph is FHIR-oriented. It's a data platform that provides a 360-degree view of a patient's health and well-being using all the data available. Health graph pulls in patient data from over 100 integrated data sources, from current lab results and clinician notes to other medical records from other systems and healthcare providers to create a complete picture of the patient's health. Not only can Health graph ingest data from an electronic medical health record to improve and secure the data set, it also natively captures data from Babylon's applications. It collects additional information from third-party data providers and our partners' various applications, creating an even more diverse set of data that can be analyzed as a unified data source. Babylon's Health graph leverages event-driven real-time data inputs, such as hospital notifications, personal wearable devices, and remote monitoring devices for major chronic diseases. Today at Babylon, over 100 different data providers are ingesting data and many times real-time across our ecosystem. It represents over 80 billion objects across our data platform. Add that to the fact that data is being received across 15 countries, that Babylon provides care for its members. That is a lot of really different data requiring structuring and standardization. We use a graphical or traversable materialization layer to store, view, and search within the 80 billion data points comprising its population health data. In this format, we can quickly and easily find trends in the data and discover hidden relationships in unrelated data sets. This provides faster times to insight and risk predictions, allowing providers to take necessary actions like sending communications and alerts to the patients. In the meantime, patients can engage with their personal health graph and take a more hands-on, informed approach to their care and health data. The health graph leverages the Babylon knowledge graph to tackle data interoperability across multiple coding standards to provide a semantic understanding of data. By adopting the CT ontology, representing clinically validated rich polyhierarchical and non-hierarchical relationships between clinical concepts as the basis for the Babylon knowledge graph, we standardize clinically coded data management across the Babylon ecosystem. Within the knowledge graph, SNOMED-CT concepts are represented by our internal extension identifiers, or Babylon IRIs, Babylon Internationalized Resource Identifiers. A SNOMED-compatible code also backs each IRI for further compatibility with SNOMED-enabled digital systems. Having our own Babylon IRIs allows us the flexibility to represent internally created concepts in line with those in the SNOMED-CT ontology. Our knowledge graph has gone through a number of iterations, beginning with Knowledgebase 1 in 2016. Originally, it was very complex, with more than 200 ontologies or clinical coding systems loaded together in a giant multi-graph, linked together by relationships, incredibly complex and complicated to make sense of the conflicts, overlaps, and redundancies, not only between the code systems, but also between the country and date versions of each. Add into that the reasons for each of the code systems for billing, diagnosis, descriptions. It was incredibly difficult to maintain and very difficult to query from a user perspective. And then the product vision changed. KB2, similar but more focused in its application. Instead of the complex web of ontologies from KB1, we wanted to start from a trusted and widely used seed source, which I'm sure you've guessed is SNOMED-CT. It covered roughly 90% of the use cases we had at the time, and then we merged subsets of graphs from other ontologies as needed. But we were still trying to merge together concepts that were seen as equal from different ontologies to create a single source of truth. This resulted in many mappings, which were resource intensive to produce and maintain. They weren't focused, and it was not scalable. It was at this point that the precursor to the health graph started to come into being. We needed to be compliant with FHIR, and we only wanted to use mappings that were reliable, coming from authoritative sources, and being able to be maintained effectively. And so to the current health graph KB current. The current version of the knowledge base is about the same size as KB2, but is based on SNOMED International with the SNOMED UK and drug extensions. We now only bring in mappings from trusted sources such as CTV3 mappings and ICD-10 mappings from the NHS to SNOMED and our own internally validated maps. We have a much more self-contained structure. We can update easily as we are more SNOMED native. The only custom layer are the IRIs themselves, which are just alternate IDs for SNOMED IDs. It's also more easy to edit. We're able to add custom concepts or relationships without the complexity exploding. Okay, as I mentioned previously today at Babylon, over 100 different data providers are ingesting data and many times real time across our ecosystem, represents 80 billion objects across our data platform. The health graph also receives thousands of unique clinical codes of varying levels of granularity from multiple classification standards. Examples of terminology standards that we receive include ICD-10-CM, ICD-10-PCS, RX norms, SNOMED-CT in its international US, UK, and other country versions, LOINC, CPT, HCPCS, and the list goes on. Individual codes within clinical coding classifications do not always have encoded relationships to other codes in our systems. They also have different levels of granularity of meaning. Therefore, if we were trying to query all data instances in the health graph for patients with chronic kidney disease, we would require listing all variations of chronic kidney disease, be it more specific codes or codes in different coding systems, to get exact matches with the ingested resources. And this is just a subset of them. A lot of problems, obviously. Missed record recall. By explicitly stating codes in a query, we will invariably miss codes that we needed. For example, the chronic condition warehouse logic uses ICD-10 codes to define query parameters, but ignores the SNOMED-CT condition codes received from care quality when we evaluate the health graph data. In a recent query on the health graph, the ICD-10 based definition recalls approximately 3,000 unique health graph member records. A SNOMED query traversing the Babylon knowledge graph of encoded relationships returned approximately 7,000 unique member records. So it definitely does make a difference. Maintaining manual queries is unscalable for analysts. Enlarging the chronic kidney disease query definition to match every SNOMED-CT code and codes from other standards we may receive in the future that may prove relevant for this definition is completely unscalable. Different definitions of clinical concepts across the business. The lack of transparency across teams means we don't handle similar members uniformly, and that's not only within the business, but also from the external data sources that we are receiving. The depth of understanding of our members is varied, which is operationally expensive. If we don't have all of the information we need, we can't give the best care that we need to. And it also means that the impact of our interventions is difficult to track. Heterogeneous member record data. On the member level, data about our members is received in different coding standards and cannot be presented in a uniform structure for health graph consumers. For example, medication data is received in multiple standards, often the same record for the same medication, including RX norm, FDB medid, NDC, and First Data Bank. Codes from different standards may hold the same semantic meaning, but computers cannot understand the similarity unless these are explicitly coded. Like analyst burden, creating and maintaining manual queries is unscalable for product teams looking after clinical support tools or member-facing applications. The scalability of machine learning models requires uniform data models with data that can be processed computationally. Like other teams, when we do not capture disparate data sources in a uniform structure on the platform level, machine learning engineers must establish anti-patterns of data processing downstream. So I work with the team that is responsible for having standard definitions in our data and unifying data from disparate sources that can be queried as a whole. We solve this with unified models and clinically validated code conversions or mappings. We transform key code systems to be immediately understood within the knowledge graph underpinned by SNOMED-CT, leveraging the rich clinically validated cross-domain relationships to effectively pull multiple standards together in a unified clinical context. This knowledge graph is Babylon's common machine-readable code language for health data. There are numerous clinical coding classification standards, but each of them are designed for specific purposes. As a result, clinical codes from different standards may share semantic equivalents, but because they're not part of the same standards, computers don't know they mean the same thing. And code mapping is an industry-accepted informatician tool used to close this gap. Not all maps are created equal, but we must have them one-to-one because we're receiving data from outside the system for a lot of the time. We need to make sure that we can recall it without having to have clinician input at the time. For example, if you had a code for unilateral foot fracture and you had the patient in front of you, you could ask them, oh, is it your left or your right? But we would have to code that to a one-to-one to foot fracture so that we know that the meaning is explicit even without the patient in front of us. Sometimes this means coding to a broader concept, but these concepts can still be used for record recall using ECL. In the beginning, we had a completely manual process, lots of spreadsheets, lots of notes within spreadsheets, and there wasn't a whole lot of reuse of the data. They were used, the mapping was created for individual use cases, and it took a long time and was very annoying. But why don't we, I get these questions a bit, use maps provided by SNOMED? The answer is we do, but only if they are one-to-one. If they are one-to-many, then we go in and validate them as to the best concept for our mapping, even if that means going broader. Why don't we automate the mapping process? Surely the computer can do that. We don't need to have people involved in the process, but I'm sure you're well aware the complexity and sensitive nature of healthcare data. We need it to be right. We need to have a validation in the process. And why don't we just use the text descriptions? Surely that would be fine, but no, it's to be able to do the full analytics, we need it to be completely machine readable. We use Snap to SNOMED. I won't go too far into it, but it's a wonderful product. I love it. Created by the wonderful SNOMED international team. Automated mapping suggestions available, but still with validation within the source. We use a 2 to 3 tiered process. We have usually myself doing initial mapping. We have our US clinical informatics team providing reviewing, and then we have a third level where we can take it to clinicians for to fight it out on what is the best code and what is the best way to map these processes. Mapping simplifies a pattern of code and record recall. Users can query all members who have chronic kidney disease instead of explicitly stating the codes from multiple standards matching or clinically related to chronic kidney disease, which can be thousands of codes in a single query, as we saw in the previous slide. Queries like this utilize the clinical context and relationships of the Babylon knowledge graph to drive maximal record recall. A health graph user can specify a more generic query for higher data recall without having to state specifics or regularly maintain the query. We enable this by automatically expanding queries to catch any more specific concepts like the ones specified in this query and the code variants for those. Here we see an example of a query that captures records tags with specifics using a general clinical concept query. Any disorder of glucose metabolism is requested and the specifics are recalled. It includes diabetes and any concept that is a type of diabetes. This query would also recall other children and grandchild of concepts of disorders of glucose metabolism, including diabetes, hypoglycemia, hypoglycemic syndrome, and pre-diabetes. Indeed, this is not limited to individual user queries. The AI learns from the data. Increasing the quantity, variety, and usability of patient health data will increase the power of the AI. Having a standard definition in our data and unifying data from disparate sources that can be queried as a whole with unified models and clinically validated code conversions allows for machine learning to be applied on the data. I know I'm over time. I'm nearly finished. Okay. We take that normalized data and we put it through a software development pipeline that turns that data into data products to fuel our AI in real time. This helps deliver better outcomes, not only for our members, but obviously value for our providers as well. Data is the key to unlocking better efficiencies in global healthcare systems. AI learns from data, as I said before, increasing the quantity, variety, and usability of patient health data will increase the power of the AI. AI helps medical professionals work faster, see more patients, make more informed decisions. By automating repetitive tasks, healthcare practitioners can focus more on their patients, improve the delivery of healthcare, and evolve the practice of medicine. It helps patients address symptoms, get faster information on conditions, and proceed to treatment sooner. Insights gleaned from the health graph can help providers better understand, for example, which members of the population are at an elevated risk and in immediate need of care. Proactive early intervention helps improve the quality of care while limiting the need for expensive, chronic, or later stage healthcare. This lowers the overall health costs of the populations we serve, benefiting the entire healthcare system. For Babylon patients, the health graph and knowledge graph play an important role in leveraging the power of the Babylon data platform to better understand their health. Patients can engage with the platform's natively integrated artificial intelligence models to gain deeper insights about their health and be more engaged at every step of their healthcare journey. We're bringing together patient and population clinical data in a unified way. By doing so, we believe we can provide new insights and information not only to the member, but to the clinician to take more proactive action to help either to manage you with a chronic condition to get you back into the health loop and out of the sick loop, or to keep you in the health loop altogether by using that information insight in a completely different way. And that is it. Whew, breathing.
Thanks so much, Erin. So for those in the room, if you have a question, I'll pass around the microphone. And for those online, please use the Q&A box at the bottom of your screen.
Thank you very much for this very interesting presentation.
Thank you.
You've told that your system is FHIR-oriented,
Mhm.
but many of the elements of FHIR resources which could bind to SNOMED-CT finally bind to fixed lists or old HL7 lists, starting with the gender, just having a fixed list with male, female, or undefined. So if you FHIR-oriented, what do you do? Do you map all of these elements to SNOMED-CT2? So not really FHIR-oriented there.
We're FHIR-oriented in our structure. So all of our different structures would have a FHIR structure behind it. So for example, we'd model for communications, we'd model for observations, model for conditions, etc. And then within that, if it's appropriate, we would have the SNOMED code in the codable concept field modeled within that.
Okay, so you've got the same granularity, but another type.
Exactly.
All with the
Exactly.
codable concept behind.
Exactly. So the structure of FHIR, but the codable concept of SNOMED.
So you do this mapping for all or nearly all elements.
That is the goal. I mean, obviously, it's a big goal. There's a lot of data, as I'm sure you can imagine, and we do it based on the data that we're receiving. So we'll do it in order of prioritization to how we get it, but it's a long-term goal.
Michael.
Hello.
Hello. You said that you're defining some of your own internal concepts.
Mm-hmm.
Are you modeling those with description logic axioms and classifying them to get them into the hierarchy? And if so, or not, even if not, are you doing any content requests to fill those gaps at the international level?
First, yes. Second, not yet. So firstly, yes, we do put them into the hierarchy. We do put them under a single hierarchy, under a single parent in our system when we create a Babylon IRI. There is a project coming up in the next quarter to actually go through all of the internally created IRIs and clean them up and then go through requesting them. But we've got our own Babylon extension of SNOMED.
Anyone else? I don't see anything online.
Okay.
Awesome.
All right.
Thanks again, Erin. It was great.
You.
And thanks to everyone who showed up. It was last session of the conference and it was standing room only. So amazing. Thanks again.